Hello and welcome. Today we're going to be talking about regression. We're going to be focusing a lot on linear and exponential regression in this. Now, to get an idea of what that is, before we actually jump into our vocabulary, I'm going to look at a short little example of where you might use something like this. So this is a graph of the last several times that my son had some people over. You can see here that we have people on the horizontal axis and slices of pizza on the vertical. And if I were to say to you, like, he's expecting to have 15 people over to the house at his next party, how much pizza should I order? A lot of you probably are looking somewhere over in this area. And hopefully you might say something like, I don't know, 30-ish pieces of pizza would be a good idea if you were to have 15 people. And that's a pretty good guess. And a lot of you may also be looking at this and saying, I can draw a line right through here and use this line to like maybe make a prediction. And if I do something like that and say, hey, this line goes kind of right between all of these points, then what I could do is to say, well, if I have 15 people coming, then I can just come up here and look at that. And I notice that this spot intersects at about 30 pieces of pizza. So if I have 15 people over, I'm going to want about 30 slices of pizza. And this is actually what regression is it's taking some data points and it's going backwards to create a line or a model that we can use. Now, in this case, I did something called extrapolation because I went outside my data set. You see, I had points for 3, 8, and 10, and if I go outside and I want to make a prediction for somewhere beyond that, that's extra. That's going beyond the scope of my data, and that's something called extrapolation. We'll get to this where you can write this down in a minute. And let's say that the next time he wants to have a party, he's actually only going to have 7 people over. Well, I could go up to here and I could say, well, it looks like that's about 14 slices of pizza. Because that's within my data set, it's inside of my data, that would be an example of interpolation. Don't worry about this. There's a place to write this stuff down later on. The last thing one of the last things I want to look at here is that right now, these data points are in really close to my line. But if I had a different example where my data was something more like this, like if we were to draw a line through here, you could draw a line and say, this is my best prediction model, but I'm probably not as confident about this one. See, the one on the left, the original model, these points are in very, very close, and I can feel very, very confident that, you know what, every person is going to eat about 2 pieces of pizza. I can tell that because the slope of my line is up 2 and over 1, up 2 and over 1, up 2 and over 1. So every person that comes is going to eat about 2 pieces of pizza. But when I look over here, sure, I still have that same similar slope going on, but the points are very scattered. And because they're very scattered, I'm just a little less sure of things. Okay, so this one on the left where we're very confident, this would have a very high correlation. And the one on the right would have a very low correlation. Now, keeping that in mind with our context, we're going to go back and look at some vocabulary. Regression analysis is the process of estimating a relationship between variables in the data set. In this case, our relationship was between people and the number of slices of pizza. When the data set appears to follow a pattern of some specific type of function, which in this case it was a line, that linear function, we can use technology to calculate a regression model or equation. Now, in that last case, like I said, our model would be a linear model because we could make a line. The regression model can be used to make predictions for unknown values. Like if I want to know how much pizza would I want to order if I was going to have 15 people. So I can use my past data to make a new prediction. Now, correlation is used to determine the strength and the direction of the relationship. So for what we had before, the first model we had, those points were in really close to that line. So that would actually be a very strong correlation. Correlation we have as some type of a variable, and we use R. I have no idea why we use R. I think it's because it's correlation, but I really have no bearing on that whatsoever. Now, we use R for linear regression. If we have something that's not linear regression, we're going to use R squared. We'll get to that in a minute. R is always going to be a number between -1 and 1, and 0 implies a weaker correlation, and if the number is very close to 1 or -1, that's a very strong correlation. Correlation isn't exactly a percentage, but you can almost kind of think of it that way. So, for example, if you have something that's in very tight, like our first one, that first example, let's go down and look at this. This would probably have a very strong correlation. This correlation would probably be somewhere close to like 0.98. You could think of it as like this line is like 98% good. I do want to stress correlation is not a percent. But when you're first learning things, 98%, that's really strong. This one over here might have a correlation of something like 0.5, like a 50%. The points definitely have an upward trend, but they're a little bit scattered. So less or lower correlation. In other words, this number is closer to 0. Okay? All right. Now, for nonlinear regressions, we actually don't use R, but rather we use R squared. And it's also known as the coefficient of determination. Think of this value as a percent, kind of in the same way that I was just talking about it with R. Now, an actual definition or an actual usage of R squared is to talk about the amount of variation in Y with respect to X. Don't worry about it too much. Just again, know that this R squared is like a percent. How much, like how good is the line? If you were in a statistics class, we would be a lot more precise than that, but it really is just kind of saying like the amount of variation in Y is accounted for in our model with X. Here's a few examples of some correlation, and let's go to another quick little example where we can play around with the numbers for a minute. Notice that I have 4 points here, and you can see that they're all exactly in a line, and our correlation coefficient is 1. If we start moving these around just a little bit, you can see that, well, once again, they're all very close to what would be our least squares regression line, or that line of best fit, and that's why we have a very, very strong positive correlation. If I start taking some of these points and start moving around a little so that they're not quite as close, you can see when the points are a little more spread out, maybe you wouldn't be quite as sure that this line is a great predictor. 0.63 is still somewhat strong, it's moderate, and if you were to think about circling these, you could make an ellipse around them. And so you'd be like, yeah, this is definitely positive. Our least squares regression line would be going up, and that's why this is still a positive 0.63. If we change it so that some of these points start to maybe have more of a downward situation going on here, you can see now that we have a downward situation if I were to kind of make an ellipse around these, and they're in kind of tight. They're all somewhat close to this line, and that's why we have a 0.74. And it's negative, and that's because our line is going down. I do want to show you as well that if you check that, we're going to look now at the steepness of this. So here we have a very, very strong negative correlation. It's negative, it's very close to 1, and you can see they're very close to that line. If I take and make the line much steeper, notice that my correlation doesn't actually really change. I still have almost the exact same correlation, even though I have a much steeper line. And that's because the correlation does not actually tell the steepness of the line. It only tells how close these points are to the line. Now, let's go ahead and look at one that has almost no correlation. So if we look at something like this, you can see that putting any line on here you don't really have a whole lot of confidence that a line would be a very good fit. And if I put it on, you can see it's almost a horizontal line. There's almost no relationship between the x's and the y's. An increase in x doesn't really give you any much information on an increase in y. So this is just a little thing that I found on Geogebra. You guys can absolutely play around with this if you want to play around with correlation. I just searched correlation in Geogebra. What we have here then is, again, now you guys have this written down where this one's perfect correlation. That's because these are exactly on a line. This would be an R value of exactly +1. This over here, if I could make a little ellipse around it, and that ellipse is really, really tight. This is very strong correlation. So it's close to 1, but it's not 1. So I might say this is a correlation of maybe 0.9. This one, the next one, is a little bit weaker. We can still kind of like make this ellipse, so I can see that this ellipse is trending upwards as we go, but it's much more circular. And the more circular something is, the closer it gets to no correlation or very weak correlation. So this might be a correlation of maybe like 0.5 or 0.4. It's probably a little stronger. This next one, when I try to make an ellipse around it, I really can't. This is a circle. So there's really no direction at all. And that's why this, like, you can't really make a very good line to pass through here. Each of these other ones, you could put a line in and say like, yeah, I'm okay. This next one, there's no correlation at all. This is a correlation of approximately 0 now. The next one, I can see it is trending down. And so this does have a weak negative correlation. So I'd probably say something like negative 0.4, negative 0.5. The next one, these points are in very close to this line. And so this is a very strong correlation, but it is negative. Because the line is going down, it's a negative correlation value and it's very strong. So I might say like negative 0.9. This last one is exactly on there. If we draw a line, it touches every single point. This would be a correlation, a perfect correlation, and it is negative, so -1. Now, up till now, we've really only talked about linear regression. Linear regression is commonly used in values that tend to increase or decrease at a constant rate, and they would have a slope. You've learned y equals mx plus b, and if we're using Desmos, that's how our our equation is going to be given to us in the form of y equals mx plus b. If you take another intro to statistics class, a lot of times we tend to write those as y equals b plus mx. They just start with the y-intercept and change from there. Honestly, it doesn't really matter. It's just that in different classes, we do different things. Now, not all things are linear. Some models increase or decrease by larger and larger quantities. And so when you increase or decrease by larger and larger amounts, that's more like an exponential model. So we've done exponential models before. If you recall, we looked at some examples where as one value increases, another one increases at an increasing rate, right? And if you'll recall, when we talked about money, we might have had something like this. We'd say like 0.05 and then raised to the 15th power. So this would be a compound interest where it's only compounding annually for 15 years. If we did it like this, now what we would have is a compound interest formula where it's compounding monthly at 5% for 15 years. So that's a little flashback to other things we did. But your money grows exponentially. It increases at an increasing rate. We are going to be using Desmos to do all of our calculation. The calculation for linear regression is really crazy, and I don't want to do it by hand. We can, it's just not fun. So we're going to get a little bit of practice with Desmos. First, we're going to enter the data into a new table. Okay, so the table button, we have to first hit the plus button that's right up here. So I'll hit the plus and then we'll hit table. You can see that we have x1 and y1. Then what we're going to do is next put in all of the data. So let's just type this in And what you'll notice too is as you're typing these in, um, sometimes it tries to predict. Like I didn't type that 14, it just put it there. The good news is you just keep typing over it. If that's the one you want, you can hit enter. This is really great when you have to put in like, you're going by the same amount each time, you're increasing. In this case, we're not though, right? So 14, then we go 15, 16, 18. I've got to go over to the next column and I'm going to type all of the rest of these in the Y column. Now that I have all those typed in, the first thing that I'm going to want to do is I'm going to hit this plus button, the zoom fit that we've used before. And when I hit that, I can now see what my data looks like. This data looks like a line, and it looks a lot like what I've already given you here on your notes as well. Mine's just red instead of green. If you really want, you can change that color by just holding that down, and we can even make these dots a little bit bigger if we wanted to. There, now it really looks like what we had before. Okay, so there's a couple different ways that you can get the linear and the exponential model. I'm going to show you two different ways. If you're using Desmos in test mode, if your teacher makes you use test mode, then you're probably going to have to do it this way. So for a linear model, we're going to type in y1 tilde mx1 plus b. And for an exponential model, we're going to type in that y1 tilde ab to the x1 power. To determine which model fits better, we're going to type both in, and then we're going to compare the coefficients of determination. Remember, the coefficient of determination is r squared. We just look to see which one has a higher r squared value. Now, I do want to let you know that in real life, just comparing the r squareds is not the way to go. We actually need to be reasonable about it and decide if it should be a linear or an exponential model, and there's context for it. We'll come back and look at that in a minute. In the case of this class, or in the case when we have no context at all, we just have numbers, then this is what we go with. We go with just comparing r squared. So let's look at how we can type those in. On Desmos, I'm going to go down to the next line. So I have my data in, and I'm going to go down to the next line. And I have to type this exactly, y1 tilde mx1 plus b. So I will type y1, and then tilde is in the alphabet side. So I come over here, and then just at this bottom row, right above this arrow is our tilde. So tilde mx1, and then I do plus b. This is a lot easier if you're on a computer because you don't have to go back and forth between those, but it's still not that bad, especially for a free calculator. The next thing that you'll see now is we have all of the same data here as what I have on your paper already. So you can see we have our r squared is 0.9837. We have the m, we have the b, and we have the r. If I was going to write this as an actual regression equation, it would just be, remember, it's y equals mx plus b, so we identify the fact that our m is 2.77 and our b is 1.57. So we'll just round to probably 2 decimals is going to be sufficient most of the time. Don't forget your x, y equals mx plus b, 1.57. So there's our linear regression model for this equation. And in this case, it represents this blue line, or it was black, and now I'm making it blue. For those of you that may have had a statistics class or you plan on taking a statistics class, just understand that when we make linear regression models, we actually put a little hat on there. You sure don't need to for this class. Just be aware that you might run into that, especially if you look up help on some other websites. We put a little hat to just say, hey, this is a prediction model. This isn't deterministic. This is a prediction. And then next, we're going to go to our exponential model. So I'll come down to the next one, and I'm going to type in just exactly what we had for the exponential model, which is y 1 tilde a b, and now I have to use this a to the b power. You can see it's actually the fourth one over in this row. So it goes x, y, a squared, and then a to the b. That puts that up into the exponent. And this is where I've got to type in x1. There we go. And this has put on now a green line. You can deselect these so that you can see these. I shouldn't say line. This is a curve. So this is our exponential growth model. And all we're going to do then is, once again, we have all this same data. It's just given to us, we have our a, our b, and our r squared. Notice there is no r. R is only for linear models. But we can use r squared, which is the coefficient of determination. So we're going to go ahead and write our equation here just for a little extra practice. And we have y equals ax plus b. So 15.25 if I round to 2 decimal places. B will be 1.07 and then to the x power. So I like to put my little hat on there. Again, you absolutely don't have to. So we have our two models. And then the last thing that I do want to show you is that when we compare our r squareds, notice that the linear model is a better fit because it has a higher r squared. The r squared for the linear model is 0.98. The linear model the exponential model is 0.97. So this is a better fit. Okay. Again, I do want to stress that normally you should take context into consideration. Okay. But for this class, we're really just going to be looking at the r squared value and say, look, this is a better fit because the r squared is higher. So let's look at a couple examples. These are good for you to type in and go from there. So I'm going to clean all this data out. I'm just going to hit backspace on this, delete it all out. You could just delete the whole thing by hitting the X. I should have done that. And then you add a table back in, right? So now we type all these in and we'll go from there. Now that these are typed in, you want to go ahead and type in your y1 tilde mx1 plus b. Quick little tip, if I hadn't deleted these out and just left them in here in my lines 2 and 3, I would already pretty much be done. But I did delete them out. So now I'm going to type them all back in again. All right, now that these are typed in, I am going to write them out because our directions do in fact say calculate linear and exponential models for each data set. So we've done that, and now I'm going to write those out. The next thing that I will do is it says indicate which model is a better fit for the data. So to indicate which model is a better fit for the data, I'm just going to label it, or I can write it out and just say a linear regression model is a better fit because the r squared is higher, right? We know that this is 0.98, this is 0.91, and then because of that, this is stronger. It's a stronger correlation. It's a better fit. That's all. Something else to kind of note here is I see that this is increasing by 9 for an increase of 4. This is increasing by 3 for an increase of 3. And if we check these, we notice that there's not drastic changes here on any one of them. For equal changes in X, we're getting similar sized changes in Y. Not exactly, but close. When you look over at this next one, equal or similar size changes in X, a change of 1, a 2, of 2, a change of 2, change of 1, change of 3. But notice the change in Y. This is going by plus 4, plus 12, plus 63, plus 200, plus 370. Nope, sorry. Some goes up by some. How about 234? Yeah, probably. I don't know. But you can see what's happening is these are getting larger and larger and larger. The changes are increasing at an increasing rate for similar size necks. That tells me that this is going to, even before I graph it, this is probably going to be an exponential model. We can identify that even just from the table. Let's take a minute though and get these all typed in. This time I'm going to leave the line that I have for 3 and the line that I have for 2. I'm going to leave those in there and just go back up and type in my new data. Now that my data is typed in, I'm going to hit my zoom fit so I can see it better. And wow, when you look at the line and the curve that we have, this line does not look good at all. That line doesn't seem to fit our data at all. And when we fit our curve on here, this looks like it does. This looks like it fits it almost exact. And if you compare the R squareds, you can see the first R squared is 0.55 for the linear model, and it's 1.01. Oh, sorry. And it's just 1. R squared equals 1 for our exponential. So the exponential model is definitely better. I am going to take a minute and write them out, though. All right, we've got this all written out. If that 2.00 bothers you, if you want to go out to 3 decimals on that, you can absolutely do that. Maybe you don't like that I rounded it that way. Being more precise is never really a bad thing. So it wouldn't be wrong to say that. It's just if I was going to round it to 2 decimals, that would round to 2.00. Then what we would say is, look, an exponential model is a better fit because we have a much higher R squareds when we compare these two. Okay. If you want, you can also put your little hats on here. I didn't over there before. Again, you absolutely don't have to. I'm just very used to doing it, and so I have to either consciously do it or not. But anyways, that's that. That's pretty much the whole lesson. That's doing all of our linear regression. I also did mention that there's a way to do these without typing it in. I said there's 2 ways to do this, and we've talked about one of them, which is to type in y1 tilde. You're going to have to do that if you're in Desmos test mode. Now, if Desmos made an update and that's not the case anymore, then cool. But if you look up at this little icon that I have, it's just to the left of x1. Let's see if I can't. Okay. So it's this. Oops. It's this icon right there, the one that looks kind of like little some dots with a line through it. Well, that's actually exactly what we're doing. A bunch of dots, and we're going to graph a line through it. So if you tap that, it automatically just puts a line on there for you, and it gives you the linear regression. And if you tap the little drop-down arrow, you can arrow down to exponential regression. And that is so much easier. If you're using standalone Desmos, I would probably do this all the time. I started out with the one that takes a little longer because I want to prepare you if you ever have to use Desmos in test mode. But as you're doing these in your homework, or if you know your teacher not going to do that, then just do this. Tap those 3 little dots, or those little dots. The icon's not there anymore, but you tap that, and then it gives this to you. Here's the exponential. Go to the drop down. There's the linear. All the data is right there. All right, let's keep going and talking about 2 more examples here. Once your regression model has been calculated in Desmos, you can make predictions. To predict an x value, you're just going to type in the y value into a separate line, and that's going to create a horizontal line on the graph. Then you're just going to find the point where the horizontal line intersects the regression model. If we want to do the opposite is true. Predict a y value, we're going to type an x value in, get a vertical line. We look for the point and where those intersect. Now you might say, wow, that's a lot. What? We actually already did this. Okay. Remember back with our pizza example, what we did was we said, why don't we graph this line straight up here and we'll look to see where this intersects. If I know that I have 15 people, and remember x is X was people, and Y was pizza slices. And if I know that X was 15, then I would just type in X equals 15. That would put a vertical line on there, and I look to see where that intersects, and that would be at about 30. So we did this. If you were to type X equals 15, that just puts a vertical line through 15, and then we look to see where that intersects our graph. If we had some amount of pizza and I was to tell my son, hey, we know that we have 25 slices of pizza. I know that's really random, but if I knew that y was 25 and I had 25 slices of pizza, I could come to 25 and say y equals 25. That tells me that we could invite somewhere between 12 and 13 people. So I'd probably invite 12 people. Hey, we have 25 slices of pizza. You could invite about 12 people. Okay. So we did this, but we're just going to do it on Desmos now. Here's our new problem. And let's go ahead and get our data entered into Desmos. Remember, minutes in the burn zone is going to be X, and calories burnt is going to be our Y value. So get these typed in. Now that these are typed in, I'm going to hit the magnifying glass so that I can see what's going on. And just looking at this, this is going to be a linear model. Also, it makes sense that it's a linear model because it wouldn't make sense that as you increase your minutes in the burn zone that your calories burned grow exponentially. That just doesn't really make sense. But I'm going to do this kind of the faster way by tapping that little icon that has it has those 4 dots and the line through it. If I tap that icon, it automatically fits a line. Calculate a regression model. Right there we have the model. It writes it out for us. There's our model. And interpret the slope. Well, remember, the slope is actually rise over run, or y over x. And if we look at what we have here, we have calories burned, and then our x value is minutes. So it should kind of make sense that our slope of 14.61, which by the way, you can always turn any number into a fraction by putting it over 1, this means 14.61 calories per 1 minute. So if we were to interpret this slope, here's a nice, maybe kind of formal way of saying it. For each additional minute of time spent in the burn zone, we can expect about 14.6 more calories are burnt. Maybe a little more informal way of saying it, we're going to burn about 14.6 calories per minute. Okay, so one's a little more formal, the other one is a good contextual, hey, I understand what's happening. Okay. Also, I want to point something else out here, and that is that if we look here at time 0, we can see that at 0, it says we've burnt 16.69 calories. The thing that I want to point out about this is our models are maybe good, but they might only be good for certain time periods. This one doesn't really make sense. It doesn't make sense to say I've exercised 0 minutes and I've burnt 16.67 calories in the burn zone. Now, I realize that our body metabolism is always going and we're constantly burning calories, but that's not what this means. Okay, so in this case, this doesn't really make sense to talk about at time 0 we burnt 16.69 calories. It's true for the model, but remember that is extrapolation. Extrapolation is when we go outside of our data set. Our data set goes from 10 minutes all the way up to 50 minutes. If we want to make a prediction anywhere from 10 minutes to 50 minutes, we can feel pretty confident that our prediction is going to be very close. If we want to go lower than 10 or higher than 50, that's where we maybe have a little bit of concern, and that's going to be extrapolation. Extra means goes beyond the data. Predict how many minutes a person spent in the burn zone if they burned 362 calories. Now, 362 calories is a Y value. So when y equals 362, all I'm going to do is go back here. I'll go to a new line and type that exact thing in. I'll say y equals 362. I have a horizontal line that passes through there, and if I just tap that little gray dot, I can zoom in on it if I want, but where these intersect is this ordered pair. It's 23.64, comma, 362. So when y equals 362, x equals 23.64 minutes. And if you want, you could then say about 24 minutes, right? When you've been exercising for about 24 minutes, you'll have burnt about 362 calories. Next, we're going to predict the number of calories burnt if a person spends 45 minutes in the burn zone. So 45 minutes, that's x equals 45, right? So when x equals 45 minutes, y is going to equal, well, let's find out. First, I'll get rid of that. And then we'll say x equals 45. Now I've got to move this around a little bit, and there it is. There I can see x equals 45. My green line is 45 minutes, and if I just tap right where those two intersect, I get that ordered pair. Y equals 673.98 calories. Okay, so when x equals 45 minutes, y equals 673.98 calories. And so what we can say is about 674 calories are expected to be burnt when exercising for 45 minutes. And that's it. Now, we also need to look at this a little bit more yet too, because if you look at this problem, it says, what about someone who spends 300 minutes in the burn zone? Ooh, okay, well, let's go ahead and look at that. When x equals 300, y equals, okay. Let's just change this from 45 to 300. 300, of course, is 5 hours. So exercising 5 hours straight. We really got to zoom out. And if we look at this, we've got 4,398.64. So when somebody exercises for about 300 minutes, they would expect to burn about 4,399 calories, or almost 4,400 calories, right? And what we want to think about is how confident do we feel with that? So, that data point is really far out there. That I don't know about. I mean, maybe your body changes a little bit with how it burns and starts to conserve energy if and staying in the burn zone. I don't know. I don't do the exercise science all that much. All I'm saying is when you make a prediction that far out, you're probably not overly confident, or at least you're not near as confident as you would be for if you're making a prediction somewhere within the data set. So for this last one, which prediction would you expect to be more accurate? Well, we would expect the one from we would expect the 45-minute one to be more accurate because it's interpolation. It's inside the data set. It's actually very close to the center of our data set. If we're making a prediction from within the data set, we can usually feel more confident than if we're making a prediction for very far outside. Sometimes we want to predict the future, and that's fine, but um, just know that that's not always overly accurate. And a really one of my favorite examples of this is back in the 1830s, the Swedish Navy estimated how many trees they would need to continue producing their ships, and so they planted 300,000, I think it was, white oaks back in 1830, and then in I think it was like 1980 they got a letter that said, "Hey, your trees are ready." And they had 2,000 years of ship making where it was constructed with wood, and so they were making predictions even with a lot of data, but they were predicting 150 years into the future because that's how long it takes for these white oaks to grow and mature. And so they made this prediction, and clearly technology has changed between now and then, and the Swedish Navy didn't need this wood anymore. And then I believe they just turned it into a national park, and they use the wood for other things. Like sometimes they'll make some furniture out of it. You have to have special permit for using it. We actually have several forests like that in the United States as well. I know there's one in Indiana, as my home state, and they use them for refurbishing like the USS Constitution, some of those old wooden naval vessels. So I do kind of appreciate the fact that these trees were originally going to be grown for war, and now they're these parks that are just beautiful, and people can go through them, and they're also used for preservation of history. Yeah, quick little tidbit. Sorry if I wasted your time, but look it up. It's pretty fascinating. All right, the next thing that we're going to look at is a contagion. A contagious disease is spreading through a large population. Health officials record the estimated number of infected each day after an initial outbreak. Let X represent the number of days since the outbreak began, and we'll let Y represent the number of infected individuals. Gosh, I could never imagine this happening, some type of an outbreak. Calculate a regression model for this. Well, again, just right from the start, when we look at the changes for equal changes in X, these are just going up by 1 each time. When we look at the Y, this is increasing by 4, and then by 8, and then by 15, and 31. Well, those are some special numbers. But you can see they're increasing at an increasing rate. This is going to be an exponential function. But let's go ahead and get it put in, and we'll look at the data and make our decision from there. Now that the data is put in, I'm going to tap the magnifying glass to do our zoom fit. And yes, this is definitely a curve. This is an exponential function. I'll tap the little icon to do the linear regression. So we'll tap that. And notice that it just puts in my linear. I said linear, but we're going to do exponential. This is a curve, so we want the exponential regression. We come down here to the drop down, and we'll look at exponential. Of course, you can see this r squared is 1. The other r squared was 0.79. It's definitely exponential regression. Let's go ahead and get our equation written out. Again, if you want to go out to 3 decimal places, you can. This would just be 1.90. If you round it to 2 decimal places, because it's 898. Next, we interpret the meaning of the growth factor. Our growth factor is this 1.90. And so that just means that every single day, every day that passes, we multiply the previous value by 1.9. And back from what we did before, you might recall that we said like 1 plus r. This was quite a while ago, and then r is our growth rate. So if we were interpreting this, you might say this: for each increase in 1 day, we expect the infected individuals to be multiplied by about 1.898, or about a 90% increase. If you were going to just kind of simplify it even a little bit more, you could say the infected individuals will increase by about 90% each day. That's kind of a little bit easier, a little bit cleaner way of saying this. Next, predict when there will be 1,000 individuals infected. So we'll come down here, and so 1,000 infected individuals, that's y equals 1,000. Because days are x, infected people are y. So I'm going to come down and just type in y equals 1,000. Now I've got to zoom out a little bit, and we could say this. So this looks like x equals 8.36 days. So predict when there will be 1,000 individuals. I don't know, sometime between 8 and 9 days, right? That's when we would expect to have around 1,000 infected individuals. And again, this is extrapolation because it's going beyond the scope of our data. Our data only goes up to day 6. So for part D, it says predict the number of infected individuals after 7 days. You know, one thing that we could do if we didn't want to use Desmos or didn't want to use the graphing, notice that 7 days, that's x equals 7. We could even just say 4.70 times 1.90 to the 7th power. And if you do that, you're going to get about the same thing that Desmos is going to tell us by tapping on the graph. It's just much easier to use the graph and use Desmos if you're permitted to do that. When we tap on that, we get 417.6. And so after 7 days, we would expect about 417, maybe about 418 individuals. Now, what does this model suggest would happen if this kept spreading indefinitely, like maybe 2 years? You know, if we try to do that on our graph, we actually, because the x-axis is only the number of days, and so if I try to put in, 2 years, so 365 times 2, 365 times 2 is 730. And if we try to graph that 730, it doesn't like it. I can't really zoom out very well. Like there's that, but to find where these intersect is crazy. So, let me just show you real quick. If I were to use my equation and say y equals 4.70 times 1.9 to the 730th power, you can see we get a very large number, and this number does not make sense. This is a ridiculously large number. This is more atoms than there are in the entire universe, let alone people. Like people max out right now, I think around 7.5 billion people. So clearly that doesn't make sense. This disease can't continue to spread and grow past that amount. So it's unrealistic because there's only about 7 billion people in the world. We can't infect more people than what there are. And that's because a lot of exponential growth models do tend to tail off. They'll grow exponentially for a while, and then eventually they kind of stop growing so fast. And let's look at an example real quick with some COVID numbers. These are the cases of the cumulative cases as reported in the US. I believe this is from the World Health Organization from January 20th, 2020 until pretty much the end of the year, so just for the year of 2020. And as you look, yeah, this looks like this fits a pretty nice exponential model. But what happened as we get up here around 20 million infected, give or take, if we look out and we start to look at past that data, notice that what happens is that tailed off. So right here is kind of where I cut that off, and then you can see that the number of infected continued to grow, but they grew at a decreasing rate. And so this is our logistic growth model. It didn't continue to grow because people started putting on masks or doing other things, social distancing and all the other things that went into effect to try to slow the spread of this virus. And as you look, like there's interesting stories that happen because then you can see as well that from certain time periods. Even after that, we get back into exponential growth again. What happened during this time frame was people maybe went back to work, stopped wearing masks, did other things. We also had the vaccines, and that's part of what also stemmed the tide. So it's not easy to just say like, oh yeah, this model predicts the future, because if you just ran an exponential model, then and it kept growing exponentially, then probably everyone in the whole world would have been infected after like a year and a half. Like it just would have kept growing. But we did things to slow that spread. So you can see that overall this is a little bit of a logistic. There's some exponential and then it turns, and it's exponential again and then it turns. So it's not just one model. And this data does only go up through 2022. That's why we have this down here. This is just a general logistic growth model. We do have a carrying capacity. We're not going to get into this in this class, but just understand that a lot of exponential functions don't actually keep growing exponentially forever, because you run out of people, or you run out of space, you run out of things, whatever it is, you tend to run out, and then the growth slows. I hope this was helpful. I hope you were able to learn a little bit about this. And remember, with Desmos, the key really is to make sure to just tap that little icon so that it gets you this drop down button, and then do linear and exponential. It's pretty straightforward. So good luck. Have fun.